So in the previous lecture, basically got to this equation using momentum balance. So this is basically force. This is basically mass times acceleration on this side, and then on the other side, this is essentially force. So this particular equation can also be broken down into components. So using the fact that U equals Ux, Uy, Z, and of course likewise for F vector. So breaking this down by components, this equation also implies the following: that for each component, this equation also holds. So the next step is to differentiate, take this d by dt, and actually do the differentiation on the left side of the equation. However, this is complicated by the fact that the volume, W over which is being integrated, is actually moving and potentially even distorting itself in space. It actually has a time dependence. So it may move to another location, and it may actually even change in shape as it moves, because it's basically being carried along by the flow of the fluid. Since this is following the W volume is in fact following a particle that's moving with the fluid. So the way to deal with this is to use Leibniz rule. So by Leibniz rule, ended up with the following. And Leibniz rule basically says, in general, I have a time derivative of a time-dependent volume that depends on t. I'm not going to write the three integrand signs. I'm just going to write one. However, since it's a volume, that implies that they were in fact three. Then I have a generic scalar field that depends on space and time, and integrate this over the volume. Then this equals another integral over the volume that's time dependent, scalar field, space and time dependence again, integrated over its volume, plus a surface integral. So this is an integral not over volume but a surface. Surface is time dependent, so this is basically the surface of the volume. So if this is the volume, and the volume, time-dependent volume, the surface is this thing. This is the surface of the volume. That also depends on time. So this integrates the function that depends on space and time over the surface of that volume. And then this is multiplied by u the dot product with the surface vector. So basically, so this is the volume moving in time. The surface vector is the normal to the volume. Could also write ds vector as ds vector equals n hat dA. So that where the n hat is basically the direction of the surface vector, and then the dA is the area of the volume, little area block of that volume. That's another way to write this. So what's going on? And then the u is actually the velocity of the surface. So it's presumed that everything inside the surface is moving at a velocity dependent upon this u field. So this u vector field depends on space and time, and it basically exists in the space. And every point on this space is basically moving at a velocity dependent on where it is located at that exact moment. So the u is actually the velocity of that point in space and time on the surface that's determined by the overall velocity of the vector field. So basically, surface is moving with a velocity of u depending upon the location of the point on the surface and the time at each point. X vector on the surface at time t. So what this essentially does, and go to the wheel. So the concept is basically of this vector is there's basically two parts. So go ahead and cut this again. So basically there's this integral and there's that integral. So there's the volume integral and the surface integral. So looking at this in more detail, start out with, let's actually start with the volume integral. So the volume integral for this field, whatever it is, depends only on how it's changing with time. So if this field was in fact the u field, the velocity field graphed here, at different times the velocity changes. So that in fact changes what this integral looks like, and that's just being caused by the change in the velocity field itself. However, the velocity field doesn't just necessarily change because the velocity field itself changes. It may also change because the blob does something. So the blob could deform. It could move into a different shape. And the other thing the blob can do is the blob can basically move around on the velocity field. If the blob is either moving on the velocity field or deforming itself, then this surface integral is the one that actually takes that into account. So back to the, okay. So basically this is the Leibniz part. And it takes it, Leibniz takes it to this equation. So the next thing to do is basically apply this, change this equation a little bit more, because this has a surface integral. So the next step is actually to get rid of the surface integral. Because it works out better to have the whole thing just be expressed in terms of volume. So I can take the surface integral, surface dependent on time, with the velocity field which also actually depends on space and time. Surface. And going to transform it to something that depends on the volume. And I'll go sigma. So the concept of how to do this is basically to use Gauss's law. So Gauss's law basically says in general, if there's an equation that depends on a surface with some vector field dot product with that surface, this thing actually equals an equation that depends on the volume, and it's basically integrated over the gradient of the vector field. So this is a fairly fundamental theorem. So the other thing to do, so this basically takes this guy and transforms it. So this is the gradient of S. I'm just going to write this out without all the T's, save some time. So sometimes making that doesn't look right. So gradient of S over the surface times the U vector so this is basically a vector, which looks like that guy. And so now this equals 1 over the volume, and then you have the gradient, this guy, times U. And now it's integrated over the volume. That, and then the next part here is to basically just look at that. This is just standard algebraic manipulation for calculus. So gradient dot product of this guy, which is scalar field times the vector field. This thing actually equals scalar field times the gradient of the vector field plus the vector field dot, no, that's not the gradient, that's actually the divergence of the vector field, and this, yeah, this is the gradient of the scalar. So the divergence of the combined vector field, and then the scalar field, the divergence of the vector field dot product with the gradient of the scalar field. Okay. So basically you want to take this and basically say that if we work this all out, this thing actually equals gradient of the velocity, and then put this guy in. Divergence of the vector field dot the gradient of the scalar field times integral which is integral over volume, and that actually equals surface integral. Okay. So the next thing to do here is to basically write out the full derivative. So going back up here, have the derivative with respect to time of this side, and this will now be written out completely as a volume integral, using this to replace the surface integral there. So, writing this out fully as a volume integral, time derivative, the volume, and scalar field that depends on space and time, integrated with respect to volume equals another volume integral, but this time the time derivative is now inside the integral, so this is a partial derivative just with respect to time of the scalar field that was space and time dependent. And then added to that is basically all of this from the surface equation, which is again the scalar field and times the gradient. Actually, I think that's the divergence of u. And on top of this, actually I'm going to switch the dot products are invariant, so they can be done in either order. So this is the gradient of the scalar field, dot product with the velocity field, space and time, and that is integrated over the volume. So this has now been converted from a volume integral into another volume integral, but this time basically the time dependence has been broken out. So it actually turns out the first term depends on time, and then the terms from the surface integral actually depend on the velocity field, as well the time dependence enters into the rest of the integral. So, checking this to make sure I got it down right. Okay. So the next step in doing this will be to basically set up this equation and then put it back into the original Euler equation.